Right now, something built in 1977 is drifting through interstellar space. It is no longer inside the solar system. It has crossed the boundary where the sun's influence ends and something older begins, and it is still sending data back to Earth. Voyager 1 and Voyager 2 were never designed to survive this long. Their computers are weaker than a modern calculator. Their power supply is fading. The engineers who built them have retired. Some have passed away. But the spacecraft are still moving, still transmitting. And what they found out there was not silence. It was a boundary, a wall of compressed plasma marking the edge of the sun's domain. It was temperatures thousands of degrees hotter than our models predicted. It was a magnetic field that refused to behave the way physics textbooks said it should. And it was something even stranger. Waves moving through interstellar space itself. Vibrations in the thin gas between stars. When converted into sound, they form a low, rising hum, a signal from a place no human has ever been. The universe is not quiet. Voyager proved that. Tonight, we're going beyond the edge of the solar system, using real data from instruments drifting 14 billion miles away to understand what actually exists in the space between stars. Not speculation, not science fiction, reality. And it's stranger than anyone expected. Part 1. The mission that outlived every expectation. The engineers who designed Voyager in the late 1960s and early 1970s were not thinking about interstellar space. They were thinking about survival. Getting a spacecraft to Jupiter in one functional piece would be considered a major achievement. Making it all the way to Saturn would be extraordinary. The idea that either spacecraft would still be operating in the 2020s, let alone sending back meaningful scientific data from beyond the solar system, was not part of the planning conversation. The original mission was ambitious enough on its own terms, a rare alignment of the outer planets, one that occurs roughly once every 175 years, created a window where a single spacecraft, using the gravitational pull of each world as a slingshot, could visit Jupiter, Saturn, Uranus, and Neptune in a single continuous flight. Without this alignment, reaching Neptune with 1970s technology would have required either decades of travel time or fuel quantities far beyond what any rocket could carry. NASA launched Voyager 2 first on August 20th, 1977, followed 16 days later by Voyager 1 on September 5th. Despite the numbering, Voyager 1 was designed to travel a faster, more direct route. It would reach Jupiter first. Voyager 2 would take the slower path that allowed it to continue onto Uranus and Neptune. Both spacecraft carried a suite of scientific instruments: cameras, magnetometers, plasma detectors, cosmic ray counters, radio antennas, all carefully tuned to study the environments near the giant planets. They also carried something else: a gold-plated copper disc, 12 inches across, containing 116 images, nearly 90 minutes of music drawn from dozens of cultures, greetings spoken in 55 languages, and recordings of natural Earth sounds. Whale song, wind, rain, the sound of a human heartbeat. This was the golden record, a time capsule addressed to whoever or whatever might someday find these machines drifting through interstellar space. The scientists who selected the record's contents, led by the astronomer Carl Sagan, understood they were probably sending a message no one would ever receive. The odds of any intelligent civilization intercepting a small probe moving through the vast dark between stars are essentially zero. But the act itself mattered. It was a declaration. A species on a small world had reached out beyond everything it knew and said, "We are here. We made this. We were trying." Voyager 1 flew past Jupiter in March 1979, returning images of the Great Red Spot in detail never seen before, discovering active volcanism on the moon Io, and revealing that the moon Europa was covered in a cracked icy shell that concealed a possible liquid ocean underneath. It reached Saturn in November 1980, photographed the rings in stunning resolution, and then, following a gravitational assist that flung it sharply upward out of the plane where the planets orbit. It began its long climb away from the solar system. Voyager 2 followed its own path through the planetary system, visiting Uranus in 1986 and Neptune in 1989. The Neptune flyby gave us our only close-up images of that planet and its moon Triton, a frozen world with geysers of nitrogen erupting from its surface. After Neptune, Voyager 2 angled downward from the ecliptic plane and began its own long journey outward. By the early 1990s, both spacecraft had passed all the planets. The cameras had been turned off to conserve power. But the remaining instruments, the ones measuring fields and particles in the space around the probes, kept running. And the readings they sent back began to get strange. Part 2. The first signs that something was out there. For decades after leaving the planets, Voyager travelled through the heliosphere, the enormous bubble of influence created by the sun's solar wind. This wind is not gentle. It streams outward at roughly 1,000,000 miles per hour, a continuous torrent of charged particles, electrons and protons and heavier ions, blasted off the sun's surface. This wind pushes against everything around it, inflating a vast region of space where solar particles and the sun's magnetic field dominate. Scientists had known about the heliosphere for years, but they had never directly measured what happened at its edge. Their models predicted a gradual and relatively orderly transition. The solar wind would slow, weaken, and eventually yield to the interstellar medium, the thin material drifting between stars. What Voyager found instead suggested that reality had not read the models. The first major anomaly came as Voyager 1 entered a region called the termination shock. This is the zone where the solar wind, having travelled billions of miles from the sun, finally slows from supersonic to subsonic speeds. Scientists predicted the termination shock would sit at around 90 astronomical units from the sun. Voyager 1 crossed it in December 2004, but at 94 astronomical units. Voyager 2 crossed it in August 2007 at only 84 astronomical units, 10 units closer than its twin. 10 astronomical units. That difference represents nearly 1 billion miles. No model had predicted that asymmetry. The heliosphere was not a neat sphere. Something was squeezing it from one side. Crossing the termination shock was not a clean event. It was turbulent. The solar wind did not simply slow down. It stuttered, fluctuated, surged and dropped repeatedly over weeks before settling into its post-shock behaviour. Beyond it lay a region no theoretical framework had anticipated. The solar wind, now slowed to a fraction of its previous speed, entered a thick, churning zone where solar and interstellar particles coexisted in turbulent competition. Scientists called it the heliosheath. Voyager's cosmic ray detectors began registering a peculiar pattern in this region. Cosmic rays are high-energy particles that originate outside our solar system. The debris of exploded stars, accelerated to nearly the speed of light by the shock waves of supernovae. As Voyager moved outward, scientists expected cosmic ray counts to rise steadily and smoothly. They did not rise smoothly. They rose in steps. Levels would climb, hold for months, then jump again. Each plateau corresponded to a different region of the heliosheath, each with its own shielding properties. The boundary was not a single wall. It was a series of nested zones. Engineers cross-checked every instrument. Everything confirmed. The readings were real. The solar system's protective structure was more complex and layered than anyone had imagined. Part 3. The Magnetic Highway and the Temperature Mystery. As Voyager 1 moved through the outer heliosheath in 2011 and 2012, its magnetometer registered something genuinely puzzling. The magnetic field lines began to allow particles to move in a new way. Rather than being deflected or trapped, both solar and cosmic particles were streaming in opposite directions along the same field lines simultaneously. Scientists named this structure the magnetic highway. a corridor where the outermost solar field lines were connecting with interstellar field lines. Solar particles leaked outward. Cosmic ray particles flowed inward. The two streams coexisted in the same space. This region had never appeared in any heliosphere model. But the magnetic highway was not the strangest thing Voyager found. That distinction belongs to the temperature data. As Voyager approached and crossed through the heliosheath, scientists expected temperatures to decline. The solar wind was decelerating, slower. Particles mean lower kinetic energy, which means lower temperature. This is basic physics. Instead, temperatures climbed. Near the termination shock, plasma temperatures reached approximately 100,000 degrees Celsius. In the outer heliosheath, measurements returned values above 250,000 degrees in some regions. The boundary zone was hotter than anywhere closer to the Sun that Voyager had previously measured. The initial response was skepticism about the instruments. Electronics that had been operating in space for more than 3 decades, subject to extreme cold and constant particle bombardment. Then Voyager 2, travelling a different trajectory through a completely separate region of space, reported the same phenomenon. 2 spacecraft, separate instruments, different locations, same anomalous result. The explanation involved 2 mechanisms happening simultaneously. First was compression. When the solar wind piles up against the interstellar medium, kinetic energy converts into heat. The particles compress and collide millions of times per second, and temperature spikes dramatically. Second was magnetic reconnection. When field lines from the solar wind and interstellar medium meet with opposite orientations, they snap and reconnect, releasing bursts of energy that heat the surrounding plasma. The boundary is essentially a continuous chain of small explosions. The temperature mystery also connected to a larger puzzle. Why was the solar wind stopping so sharply? The answer was that the interstellar plasma was not passive. It was actively pushing back, carrying its own thermal pressure and its own magnetic field. The solar wind was not simply running out of energy, it was meeting an adversary. Part 4. The Shape of the Bubble. Before Voyager's data began rewriting the textbooks, the standard mental image of the heliosphere was something like a sphere, a bubble blown by the sun into the gas between the stars, inflated by the solar wind to a more or less symmetric shape. Voyager dismantled this picture completely. The root cause of the asymmetry is our motion through the galaxy. Our solar system orbits the centre of the Milky Way at roughly 500,000 miles per hour, completing one full circuit in about 230 million years. As we travel, we plough through the interstellar medium the way a boat moves through water. This side facing our direction of travel, the nose of the heliosphere, experiences direct pressure from the oncoming medium. The interstellar material piles up against the nose, compressing the heliosphere on that side. The trailing side stretches outward. This creates a fundamentally asymmetric shape, compressed and blunted at the front, stretched and elongated at the back. The tail of the heliosphere may not even be a single coherent structure. Newer models suggest it might fragment into multiple lobes twisted and separated by magnetic forces. The heliosphere, seen from outside, might look less like a teardrop and more like a comet with a fractured spreading wake. The heliosphere also breathes. Every 11 years, the sun completes a cycle of activity. At solar maximum, the solar wind blows harder, and the heliosphere swells outward by as much as 2 billion miles. At solar minimum, the wind weakens and the heliosphere shrinks. The 11-year cycle is also punctuated by the reversal of the sun's magnetic poles, which sends ripples outward through the entire heliosphere, distorting the boundary for months afterward. The shape of the heliosphere matters because it determines how much of the galaxy's cosmic ray bombardment reaches Earth. The compressed nose blocks more cosmic rays. The stretched tail provides less protection, as the heliosphere expands and contracts over solar cycles. The cosmic ray flux reaching Earth changes accordingly. scientists have proposed that transitions between different interstellar cloud environments can cause significant changes in heliosphere size, and therefore in Earth's radiation exposure, that may have been large enough to influence climate and mutation rates over geological timescales. Part 5. The Crossing. In the summer of 2012, Voyager 1's instruments began registering a change unlike anything seen before in the mission. On August 25, 2012, the count of solar particles dropped by more than half within a single day. Thousands of detections per second became hundreds. The change was not a gentle fade, it was a cliff edge. Simultaneously, the count of galactic cosmic rays jumped by approximately 30% within hours. The science team gathered. Had Voyager crossed the heliopause? The uncertainty was genuine. The particle data seemed clear. But the magnetometer said nothing unusual at all. The magnetic field direction had not changed, and every model predicted a rotation should occur when crossing from solar to interstellar magnetic influence. For months, the debate played out in technical meetings and journal preprints. The answer came in April 2013 from an unlikely source, an eruption on the Sun. Coronal mass ejections. Enormous explosions that hurl billions of tons of plasma into space at millions of miles per hour, travel outward for months before eventually reaching the boundary. When this one reached Voyager's position, it caused the surrounding plasma to vibrate. These vibrations occur at a frequency that depends directly on plasma density. Measure the frequency, calculate the density. The result was unambiguous. The plasma density around Voyager 1 was more than 40 times higher than inside the heliosphere. Voyager was surrounded by interstellar plasma, the ancient diffuse material that fills the space between stars. It had crossed the heliopause in August 2012. Humanity had sent a physical object beyond the solar system for the first time in history. The magnetic field mystery resolved through coincidence. The solar magnetic field and the interstellar magnetic field happened to be pointing in nearly the same direction in the specific region where Voyager 1 crossed. So when Voyager crossed the boundary, there was no rotation to detect. When Voyager 2 crossed the heliopause in November 2018 in a different location, the magnetic field did rotate. Over several days, the magnetometer registered a shift of about 45 degrees, the field gradually aligning with the interstellar configuration. 2 data points, 2 different stories. Together, they told the truth. The crossing itself was not a sharp line. Both spacecraft spent days to weeks in a transition zone where solar and interstellar particles mixed and the magnetic field fluctuated wildly. The heliopause is not a wall, it is a frontier region, a turbulent, energetic interface where 2 environments have been pushing against each other for billions of years and neither has entirely won. Part 6. What Voyager heard. In the popular imagination, space is the place where no one can hear you scream. This idea has a basis in physics. Sound as we experience it requires molecules to vibrate and carry pressure waves, and the interstellar medium is so thin that traditional acoustic propagation cannot happen. But that statement misses something important. Sound is pressure waves. In plasma, where matter exists as charged particles interacting through electromagnetic forces, analogous waves propagate through oscillations in the charge particle density. The physics is different from air acoustics, but the structure is similar, and these plasma waves carry energy over vast distances. When the coronal mass ejection reached Voyager in April 2013 and set the surrounding interstellar plasma vibrating, the resulting oscillation had a frequency of 2.6 kHz. NASA scientists converted the signal to audio, and the result was a rising tone, a whistle ascending over several seconds as the shockwave propagated through the plasma. The sound of interstellar space, recorded by a spacecraft built before personal computers existed, transmitted across more than 13 billion miles, decoded by scientists on a planet orbiting an unremarkable star in an outer spiral arm of the Milky Way. A second solar eruption in 2013 produced a similar oscillation, Scientists compared the two measurements. The frequencies matched predictions based on plasma density, confirming the technique was reliable. The plasma wave instrument was functioning as a kind of ear pressed against the medium of interstellar space. But the most unexpected discovery came when researchers looked carefully at the background data, not the dramatic spikes from specific solar events, but the quieter, continuous signal underlying everything else. Hidden in the noise, at a frequency around 30 Hz, was a persistent, unceasing signal, not sporadic, not episodic, constant. The interstellar medium was humming. The source of this background hum is the continuous turbulence of the medium itself. The local interstellar cloud is not static. It flows. Galactic magnetic field lines move through it, driving oscillations. Shock waves from distant supernovae, ancient and faded but still propagating after thousands of years, ripple through the plasma. All of this generates low-frequency waves that overlap and interfere, producing a background acoustic signature. In 2021, scientists at Cornell University identified a faint but persistent plasma wave emission at about 3 kHz that appeared to originate from the medium's own thermal energy, present continuously, not triggered by solar events. The interstellar medium maintains a low-level thermal emission all the time. Space is not quiet. It never was. We simply lack the instruments, the distance, and the patience to hear it. Part 7. The Ghost Shock. That wasn't there. Every model of the heliosphere predicted something called a bow shock. When an object moves through a medium at speeds exceeding the medium's wave propagation speed, it creates a shock wave upstream. Our solar system moves through the interstellar medium at roughly 43,000 miles per hour, supersonic relative to most wave speeds in the interstellar plasma. By the same physics that creates a sonic boom, our heliosphere should have been pushing a bow shock ahead of it. Models placed it at about 230 astronomical units from the Sun. When Voyager's trajectory carried it through the predicted bow shock region, the instruments found nothing. No compression, no temperature spike, no density change, just gradual variations extending uninterrupted through the predicted shock location. The bow shock was not there. The explanation emerged gradually. The medium we happened to be travelling through, the local fluff, a specific low-density cloudlet, has a density of approximately 0.3 atoms per cubic centimetre, roughly 100 times less dense than denser interstellar clouds. At this density, the medium does not pile up fast enough to form a sharp shock. Instead, it creates a bow wave, a gentle increase in pressure spreading across billions of miles rather than concentrated in a narrow boundary. This was a finding of the first order. It showed that the local properties of the interstellar medium are not average. We are in an unusually thin pocket of space. Our solar system has not always been here. Around 10,000 years ago, our galactic orbit carried us through a denser cloud, one with enough substance to compress the heliosphere and likely generate a real bow shock. In 10,000 to 20,000 years, we'll exit the local fluff and likely enter denser material again. When that happens, the heliosphere will compress, the bow shock will reappear, and Earth's cosmic ray exposure will increase. The absence of the bow shock was, paradoxically, one of Voyager's most valuable discoveries. Not finding the predicted feature told scientists something profound about the specific, particular, local environment through which our solar system happens to be moving at this moment in its long orbit around the galactic centre. Part 8. The interstellar medium up close. Once Voyager crossed the heliopause and began transmitting data from the other side, scientists had for the first time direct measurements of the local interstellar medium, the material actually filling the space between the stars in our galactic neighbourhood. Not indirect observations through telescopes, not models. Readings from a probe physically embedded in the medium itself. The plasma Voyager detected in interstellar space has a density of approximately 0.13 particles per cubic centimetre, more than 40 times denser than the solar wind plasma near the heliopause. The temperature of this plasma was a surprise. Scientists expected interstellar space to be cooler. Plasma temperatures in the interstellar medium range from about 40,000 to 50,000 degrees Celsius, significantly higher than theoretical models had predicted. The reasons involve compression from our solar system's motion, magnetic reconnection releasing energy continuously, and the residual heat from ancient supernovae that carved out the local bubble. The local bubble is perhaps the largest scale structure relevant to our immediate cosmic neighbourhood. Beginning around 10 million years ago, a series of massive stars in our region of the galaxy exploded as supernovae. The shock waves swept through the surrounding gas and dust, pushing material outward and carving out an enormous void extending approximately 1,000 light-years across. Its interior is filled with extremely hot, thin plasma at temperatures approaching 1 million degrees. Our solar system sits near the edge of this bubble, inside a smaller, cooler, denser structure, the local interstellar cloud, that drifts through the bubble's interior. Magnetic field measurements from the interstellar medium revealed another surprise. The interstellar field turned out to be approximately 4 times stronger than models had predicted, at around 4 to 6 nanotesla. A stronger interstellar magnetic field exerts more pressure on the heliosphere, contributing to its compressed asymmetric shape. It also controls how cosmic rays travel, guiding them along field lines and creating directional preferences in where they enter the heliosphere. Cosmic ray levels in interstellar space are approximately 9 times higher than near Earth, confirming the protective role the heliosphere plays. Beyond the heliopause, Voyager experiences continuous bombardment at about 900 million particles per square meter per second. The energy distribution of these particles also extends to much higher energies outside the heliosphere. The full cosmic ray spectrum, including ultra-high energy particles. The heliosphere screens most of these out. Without it, surface radiation levels on Earth would be substantially higher. Part 8, B2 probes, 2 stories. The fact that 2 Voyagers crossed the heliopause, rather than 1, turned out to matter enormously. Science built on a single data point can go badly wrong. A single measurement cannot distinguish between a universal feature and a local accident. Having 2 probes, widely separated in space and time, made it possible to ask a question that cannot be answered from one crossing. What is the same everywhere, and what is merely a local quirk? The 2 crossings were dramatically different in almost every detail. Voyager 1 crossed during a period approaching solar maximum, when the heliosphere was near its largest extent. Voyager 2 crossed 6 years later during a period of declining solar activity approaching solar minimum, when the heliosphere had contracted. These 6 years spanned roughly half of one complete solar cycle. The heliosphere breathed inward by billions of miles in that interval. The cosmic ray transition at Voyager 1's crossing was gradual over the preceding months, building in steps before the final jump. At Voyager 2, the transition was more abrupt. The boundary was apparently sharper at that location, compressed into a thinner zone by the local magnetic field configuration. Temperature readings at the 2 crossings differed dramatically. Voyager 1 encountered plasma near the boundary, exceeding 250,000 degrees Celsius. Voyager 2 recorded temperatures closer to 100,000 degrees. This suggested the boundary has thermal hotspots and cool spots, regions where magnetic reconnection and plasma compression are more or less intense. The magnetic field behavior was the most striking difference. At Voyager 1, no field rotation was detected across the crossing. At Voyager 2, the field rotated clearly over several days, shifting approximately 45 degrees from the solar to the interstellar orientation. If only Voyager 1 had crossed, scientists might have concluded that magnetic field rotation simply does not occur at the heliopause. Voyager 2 showed that it does, just not everywhere. Scientists could now sort the observations into 2 categories: universal features seen at both crossings despite their differences, include the increase in galactic cosmic ray flux, the increase in plasma density, and the fundamental change from solar to interstellar magnetic influence. Local features, different at each crossing, include the exact distance from the Sun, the temperature of the boundary plasma, the sharpness of the transition, and the level of magnetic turbulence. Separating universal from local is exactly what good science requires before building general theories. A model that only explained Voyager 1's crossing would be wrong about Voyager 2. A model that accounts for both and explains why they differ is more likely to capture something true about how heliospheres work in general. Part 9. Power, Silence, and the Long Goodbye. Voyager's instruments do not run on solar power. 13 billion miles from the Sun, sunlight is so faint, nearly 25,000 times weaker than at Earth's distance, that solar panels would need to be the size of a football stadium to generate useful electricity. Instead, both spacecraft are powered by radioisotope thermoelectric generators, devices that convert the heat from the radioactive decay of plutonium-238 into electricity. Plutonium-238 decays with a half-life of 87.7 years. The decay is steady, predictable, and requires no moving parts. At launch, the generators produced approximately 470 watts, enough to run all scientific instruments, the transmitter, the attitude control thrusters, and the heaters. Now, after nearly 50 years, each generator produces approximately 240 to 250 watts. The output declines by roughly 4 watts every year. There is no workaround, no augmentation, no way to slow the decline. Mission engineers have spent years carefully managing this slow attrition. Every instrument draws power, every heater draws power. When total consumption exceeds total production, something must be turned off. Each shutdown is permanent. The tape recorders were shut down years ago. The ultraviolet spectrometer went dark in 2020. Each loss narrows the spacecraft's vision, but extends the operational life of what remains. In 2017, engineers activated backup thrusters that had last been fired in 1980, 37 years earlier, and which had been sitting dormant in the cold ever since. They worked perfectly. The backup thrusters brought additional years of precise antenna pointing. Critical, because a misalignment of even a few degrees reduces the already extraordinarily faint signal to noise. That signal is itself a marvel. Voyager transmits at 23 watts, less than a refrigerator light bulb. By the time a tiny fraction of this signal reaches Earth, after travelling more than 14 billion miles, the power level is approximately 100 billion billionths of a watt. To capture it, NASA uses the Deep Space Network, 3 large antenna complexes in California, Spain, and Australia. The primary antennas are 70 meters in diameter, operating near the theoretical limits of radio detection sensitivity. Data flows from Voyager at 160 bits per second, millions of times slower than a modern home internet connection. Light takes more than 21 hours to travel from Voyager to Earth. Every command is a 42-hour round trip. Every problem discovered has already been progressing for nearly a day by the time anyone on Earth knows about it. By approximately 2030, engineers project that power output will drop below the threshold needed to reliably operate any scientific instrument. The plan is to keep the transmitter running afterward, broadcasting a simple carrier tone, a beacon that says only "I am still here." Eventually, even the transmitter's power supply will fail. The signal will fade over weeks. Then, on some specific day in the mid-2030s, it will fall below the detection threshold of the Deep Space Network's most sensitive receivers. Voyager will go silent. The scientists and engineers who have dedicated their careers to Voyager will know that the spacecraft is still out there, still moving, still carrying the golden record through the dark, just no longer speaking. Part 10. Wrong about almost everything. Before Voyager reached the termination shock, scientists were confident in their models. They had been refining heliosphere theory for decades. They had a consistent picture. It was wrong in almost every important way. The termination shock was predicted at 90 astronomical units. Voyager 1 found it at 94, Voyager 2 found it at 84. The discrepancy revealed a fundamental asymmetry that no model had incorporated. The transition from solar to interstellar space was predicted to be gradual and thin, a few million miles wide. Voyager found a transition zone hundreds of millions of miles thick, turbulent and energetic, with solar and interstellar influences mixing in complex, unpredictable ways. The cosmic ray flux was predicted to rise smoothly. Voyager found it rising in steps, with each step corresponding to a discrete boundary region nobody had included in the models. The magnetic highway appeared in no simulation. The bow shock, predicted confidently at around 230 astronomical units, was simply absent. The interstellar magnetic field was predicted to be weaker than the solar field in the boundary region. It turned out to be 4 times stronger. The interstellar plasma was predicted to be cooler than the heliospheric interior. Near the boundary, it was hotter. The magnetic field was predicted to rotate clearly when Voyager 1 crossed the heliopause. It did not because the instruments failed, but because of a coincidence of geometry that no model had considered. Every failed prediction taught something valuable. Science does not advance only when experiments confirm theories. Some of the most important moments in scientific understanding come when careful observations reveal that the elegant theory was simply wrong. Voyager's decades of anomalous readings forced an entire generation of heliospheric physicists to rebuild their models from the ground up. They incorporated magnetic reconnection as a dominant energy source. They added time dependence. They acknowledged asymmetry as a fundamental feature rather than a perturbation. They revised the role of interstellar pressure from passive background to active participant. The new models are better. They match Voyager's observations far more closely. But they are still simplifications of a reality that Voyager has shown us is more intricate, more variable, and more energetic than our best theoretical frameworks fully capture. The universe does not arrange itself for our convenience. Part 11. What comes after silence. When Voyager falls silent, it will not stop moving. At 38,000 miles per hour relative to the Sun, it will continue forward through interstellar space with no air resistance, no friction, nothing to slow it down. Voyager will coast essentially forever. In approximately 40,000 years, Voyager 1 will pass within 1.6 light-years of Gliese 445, a red dwarf star in the constellation Camelopardalis. It will not come close enough for the star's gravity to capture it. Voyager will drift past in the dark, unseen, an artifact of a civilization that may or may not still exist, carrying images of a world that may or may not still be inhabited by anything recognizable as its builders. The golden record will outlast everything else aboard. Gold does not corrode in vacuum. The aluminum protective cover will erode glacially from micrometeorite impacts over hundreds of millions of years, but the disk beneath it should remain largely intact for at least 1 billion years. The grooves that carry the audio signal will slowly accumulate radiation damage over geologic timescales, but the broad features of the encoded images and sounds may survive for an almost incomprehensible length of time. The record includes a pulsar map, a diagram showing the position of our solar system relative to 14 pulsars, whose spin frequencies change measurably over time. A sufficiently advanced civilization could use the pulsar frequencies to determine when the map was made, and by extension, approximately when and where humanity existed. The map is a return address. Carl Sagan said the record was not really intended for aliens. Any civilization capable of finding Voyager would almost certainly know more about Earth than the record could tell them. The record was for us. It forced a confrontation with the question of what humanity considers most important about itself, most worth preserving, most worth broadcasting into the dark: music, language, mathematics. Images of living things, the sound of a child's laughter, and the song of a humpback whale. Part 12. The mission that keeps giving Voyager was designed as a planetary mission. It was supposed to photograph Jupiter and Saturn and, if everything went right, maybe reach the outer solar system boundary in its final years of operation. Nobody expected it to become an interstellar probe. Nobody built it to measure the local interstellar medium. And yet, the data Voyager has sent back has generated hundreds of peer-reviewed scientific papers. It has rewritten the standard models of heliospheric physics. It has revealed that the boundary of our solar system is turbulent, asymmetric, dynamic, and energetically active in ways nobody anticipated. It has provided the only direct measurements ever made inside the local interstellar medium. It found a magnetic highway. It confirmed that the expected bow shock is absent. It measured a persistent electromagnetic hum from the medium between the stars. And it did all of this on 68 kilobytes of computer memory, transmitting at 160 bits per second, powered by the nuclear decay of a small amount of radioactive metal. The Voyager program cost approximately $800 million in today's dollars, roughly the budget of a single Hollywood blockbuster. For that investment, humanity obtained the only direct measurements of interstellar space that exist, and a scientific legacy that will inform research for decades to come. Voyager has given future missions a foundation. We know the boundary is turbulent, not calm. We know the transition zone is thick and energetic. We know the interstellar magnetic field is stronger than expected. We know the bow shock is absent in our current environment. We know which measurements matter most. The next probe to cross the heliopause will go knowing the territory. Conclusion. There is a moment that Carl Sagan wrote about, and that scientists who have worked on Voyager tend to return to. On February 14th, 1990, as Voyager 1 was sailing outward past the edge of the known solar system, mission scientists commanded it to turn its camera backward, toward the sun, toward home. From 3.7 billion miles away, Earth appeared as a tiny pale dot, less than a single pixel, barely distinguishable from the scattered light in the camera's optics. Sagan called it the pale blue dot. He wrote that every human who ever lived had lived on that mote of dust, suspended in a sunbeam. Every empire, every war, every act of creation, every act of destruction. All of it on a speck. The photograph was not scientifically necessary. It produced no new measurements about the solar system structure. Scientists took it anyway. Because sometimes the point is not data. Sometimes the point is perspective. Voyager has been giving us perspective for nearly 50 years. It is possible to know all the facts about Voyager, the dates and distances, the instruments and findings, the technical constraints and engineering workarounds, and still miss what makes the mission genuinely remarkable. The remarkable thing is the scale of the difference between what we are and what we managed to do. We're a species that has been recognizably modern for perhaps 200,000 years. We invented agriculture about 10,000 years ago. We've had writing for roughly 5,000 years. We developed physics capable of accurately describing planetary motion about 400 years ago. We built our first powered aircraft in 1903. We landed on the moon in 1969. In 1977, we built 2 spacecraft with the technology of that moment. Vacuum tubes and hand-soldered transistors, and magnetic tape storage and radioisotopes and gold-plated copper discs. And we threw them into the solar system, and they went. They flew past Jupiter and returned images of volcanoes erupting on moons. They flew past Saturn and measured the composition of ring particles. They entered the termination shock. They crossed the magnetic highway. They survived the compressed boundary of the heliopause and emerged on the other side. They detected the hum of interstellar space. They measured the density and temperature and magnetic field of the medium between the stars. Voyager 1 is now more than 14 billion miles away. Light from it takes more than 22 hours to reach us. The signal arrives at a power level so vanishingly small that finding a useful analogy requires real thought, and yet we receive it, we decode it, we understand it. Somewhere beyond the farthest boundary of our solar system's influence, in the ancient slow-flowing plasma of the local interstellar medium, there is a small machine made by human hands. It carries our music and our mathematics and our greetings and our images. It carries proof that something on Earth was alive and was curious and was reaching outward. It will keep moving, long after the last signal fades, long after the last person who built it or flew it or read its data has died, long after the buildings where the mission was controlled have been demolished or repurposed or crumbled, long after the civilization that launched it has become something unrecognizable or ceased entirely. Voyager will still be moving. The stars will change around it. Galaxies will drift. The universe will continue its expansion. And Voyager, silent and small and extraordinary, will drift through it all, carrying a record of everything we thought was worth saying, into the dark, still going.